Good morning, good afternoon, good evening. What time is it? I don't know. Depends when you're watching this. That's the weird thing about talking to a computer. I'm like used to looking at a person or a classroom, and there's nobody there. How lonely. Yeah. How do these electrons, with these particular quantum numbers and orientations, end up filling in these the spaces around the nucleus, the nuclei? We kind of know something about the quantum numbers that describe locations where they're able to stably exist in the atom. Here's a review, and you can study this at your leisure. But I certainly see a lot of patterns there. Um, but the answer is there are specific notations that we use. There's a specific notation, or a couple of variations on that. We've introduced this already, the S block, the P block, the D block. But what I do is I think about building up larger and larger atoms from hydrogen, helium, lithium, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine, fluorine, sodium, magnesium, aluminum, yada yada yada. So they all start off the same way. This capital 1 means, this large one, number 1, means it's the quantum number n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, and on and on and on. But I think about reading it from left to right. Da 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 da. And with every da, I'm adding one proton and one electron, probably one or more neutrons. Da 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 da. There's 10 dots there, and then da 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 da, and then da da, and then da 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 da. That's six. Anyways, you get the idea. And the little superscripts up here, that means 2 electrons can fit in the 1s orbital. So this one and this one. 2 electrons can fit. 2 electrons can fit in the 2s orbital. These two. And then after the 2s comes the 2p. I'm reading it line by line, left to right, as I'd read a paragraph or something. There's discontinuity in the print there, but okay. So 2p is right there. Six electrons can fit into those orbitals. It would go 1, 2, 3, 4, 5, 6. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. If I had stopped at, say, 3p5, I'd be stopping right here for this element, and the yada yada 3p5 would describe, or I should say 1s2, 2s2, 2p6, 3s2, 3p5 would describe this element right here. Or if I would stop right here, I believe this would be iron right here, and that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. I think, yeah, 3d6, that's iron right there. So depending on how large your atom is, how many protons, therefore how many electrons must fit around those protons, we describe the orientation or the location, the probability of those electrons in the orbitals, just like this. And I stop wherever I need to stop in the schemata of counting. Here's another similar patterns. S block, P block, D block. That's not describing any orbitals, but okay, we get the idea. This one's kind of nice. Check out how they listed 1s here and better make that a little bit smaller actually. There we go. 1s here, 2s, and then 2p's, and then 3s, and then 3p's, and then 4s. You notice, let's see, layer 3 has some p orbitals, but they're kind of offset, right? They're offset down a little bit. I could say because the 4s orbitals actually fill in before the orbital fills in before the 3d start to fill in. As they are so close in energy, it just turns out, trust me on this one, that's the order of filling. And let's see, layer 4 is large enough to have F's, but those F's come in right here. After lanthanum fills in a 3D1 electron, then it goes 4F1, 4F2, 4F3, 4F4, 4F5, 4F6, 4F14, and then 5D2, 5D3, 5D4, 5D5, 5D6. It's a mess when the electrons, when the atoms get so big, it all gets kind of screwy. Oh, that's, yeah, shoot, a little bit too big. S block, P block, D block. You'll notice, do you realize that these rare earth lanthanide and actinide series, actually you're supposed to sneak right in here, and this makes it, this is a long form of the table, but sometimes for these heavier elements we'll fill in these two, maybe one of the d orbitals, and then start filling in the f orbitals, and then go back to the d orbitals, and it can be a mess. It can be unpredictable. My son says something more about that in a bit. Another review of some quantum numbers, principal quantum numbers 1, 2, 3, 4. S orbitals have L equals 0. P orbitals have L equal 1. D orbitals have L equal 2. F orbitals have L equal 3. And indeed, the levels kind of split like that. I mean, in the sense that principal quantum level 1 is lowest in energy. Level 2 is higher than that. And 2p is higher than 2s. And level 3 is higher than that. 3s, 3p, 3d. But the 4s is even a little bit lower in energy than 3d. So voila, sometimes, usually I'll fill in the 4s before the 3d. Here's a representation of nitrogen. 1s2, 2s2, 2p3. You'll notice in this energy level diagram, one electron goes into 2px, one goes into 2py, and one goes into 2pz orientation orbital. And if you don't remember that, you could look back. I don't know if I have any pictures of that. I don't know if I do. So these boxes are representing the orbitals. This is the spherical orbitals, and these are dumbbell-shaped orbitals, and one electron can go in each one, and they like to avoid each other because they're all negatively charged. They do all maintain the same orientation, say a positive m sub s, positive 1/2 m sub s number, but they do spread out in those orbitals before they go back and pair up. So if I put this one right here, that'd be wrong because they're fitting there. These electrons would rather spread out in the orbitals before pairing up. But they will pair up before they go on to the next level, almost always. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. No, 5. Yeah, 3d5. And 3d5 is indeed manganese. So notice how I spread them out before I paired any of them up. But then as I was filling them in, and I mean up, then go back and go down, and then I go up, down, and then I go up, all electrons spinning in about the same way. And interesting. Alright, we'll see more examples of this in class, I'll bet, on OWL homework and the text and discussion sections. What's wrong with this? Oh, I can see several things wrong with this. Check this out. What's wrong with this? You can't have two electrons with the same spin, both m sub s plus 1/2. One's got to be up, one's got to be down. What's wrong with this? You can't have 3 electrons in an orbital. That's ridiculous. What's wrong with this? Oh yeah, this is, I think it's called Hund's rule, right? This is the Pauli exclusion principle. You can't have 2 electrons in the same quantum state doing exactly the same thing. So that violates Pauli. This violates Hund's rule. Say they spread out in the degenerate energy levels, because this box and this box and this box, 3px, 3py, 3pz are degenerate. They're all the same energy level, so these will spread out before they pair up. And this shouldn't be up here either unless it's an excited atom. If this is a ground state atom, this would be lower down here or something. But indeed, if this one got bumped up to here by a photon of energy or something, or put it in a fire, literally put the element in a fire, it gets the electrons excited. But this won't stay up here long, it'll jump right back down. So this could be something wrong with it unless it's an excited atom. Alright, let's look at some patterns. Gosh, time flies when you're busy, huh? I mean, these videos are so enjoyable and time just goes so quickly. Oh, geez. Okay, so hydrogen, helium, lithium, beryllium, boron. I just went down in order. And notice how I keep adding one to that orbital until it's filled up, and then I go to the next orbital. Yeah, the superscripts again describe the number of electrons in those orbitals. Orbitals can hold 2 electrons, but there are really 3p orbitals hidden right here, if you know what I'm saying. There's the 3px in this direction, the 3py in this direction, and the 3pz coming in and out of the paper. Go back and review your sizes or your shapes of your 3p orbitals if you want. Oh, I highlighted this in red too because this is a noble gas, something special about that filled layer. Highlighted that, that's a noble gas, neon, something special about that. Then beyond neon I go to sodium with a 3s1 and 3s2 is magnesium, and then that's 3s is full, and I go to 3p and 3p1, 3p2, 3p3. I see a pattern reading left to right. Argon's a noble gas, so I highlighted it in red. Then I go to manganese. Oh, I'm filling in my d orbitals now. D orbital all fills up. And gallium, then 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. Brings me to krypton. Interesting. There's a shorter way to write this. If you want to start with a noble gas, I write neon in square brackets if I'm going just a little bit beyond neon or something. Then what's right beyond neon is sodium, but instead of writing all this junk, why don't I just write neon in square brackets and call it good? That's like the inner core, the noble gas core of electrons in the 3s1. So sodium really only has one electron that can do anything. The rest are stuck in the noble gas inner configuration. Magnesium has 2 electrons, 3s2. Those 2 electrons can do something. The rest of them are kind of stuck in there within a neon-like configuration. More examples. Oh, geez, too far, too fast. Noble gas shorthand. Yeah, you should look at this PDF or store it somewhere on a device. You could study it again, right? Argon, after argon comes potassium, calcium, scandium, and I'm just adding electrons into the orbitals. And if you don't see a pattern there, take some time to look at it. It's a cool pattern. After all the d orbitals are filled in, then I go back to the 4p orbitals, and I finally reach krypton, the next noble gas, and I could continue on from there. So this saves you, argon, square brackets saves you from having to write this. Right. More examples. Oh, what about energy level diagrams? What does this mean? That means that sometimes we'll just see the outer electrons mentioned, not the inner core. So there's a 1s2 here as well, but I didn't mention it. And inside of sodium is neon, but I didn't mention it. Or sometimes it is mentioned actually in neon square brackets in 3s1, 3s2. I hope you see the patterns here. It all fits together if you look at it enough. So iron would look like this. Go to argon, then go 4s2 and 3d6. 4s2 and 3d6. Barium would look like this. Go to xenon, then 6s2, 6s2. For better or for worse, not all the larger atoms, even starting at copper, have exactly as would be predicted the configuration. Sometimes the copper, silver, and gold, which are in the same family, don't fit the pattern. They actually fit their own pattern. They fit the pattern of filling into one electron in an s orbital, then filling up the d orbitals. And then if I had a copper negative ion or something, then I could fill in this or go beyond that to, is it called? Zinc? Yeah, zinc has this one all filled in. But realize that copper, silver, and gold are in the same little mini family in the transitions. Look at gold. By the time you're up to this level 6s, 4f, 5d, they're all so close in energy that almost always these end up filling up first and then kind of leaving that empty or open so that I can go on. One beyond gold is, is it mercury? I've forgotten. I should go look. What is one beyond gold? I don't have time. Sorry. Yeah. I'm easily distracted. Is that all I had for you? Oh, shoot, I have more. Here's other descriptions of how those quantum numbers are described. The last one I have is this little slide here, and I don't have much time to look at it with you. Right, am I almost out of time? Almost out of time. Take a look at it sometime. Thanks, guys. See you in class.